practical voltage source is modeled by an ideal voltage source, our circuit model element for an ideal voltage source, in series with an internal resistance. It's also referred to as an output resistance. It's internal to our two-terminal device, which is a practical voltage source. Um, it's internal to that, but it's also at the output terminals. It's the output resistance seen looking back in. So the load looks back in and sees this output resistance RS. S for being in series, specifically in series with our ideal voltage source. So examples of practical voltage sources, we talked about a battery, a solar cell. The battery might be able to provide a potential of 9 volts across it, but once it starts to draw current, that voltage decreases, and it's the voltage at the output terminals, VL, that the load is going to see. So the linear relationship between our output voltage VL and our output current IL can be mathematically modeled using a KVL around the loop, where this VL is equal to, in this direction, negative RSIL plus VS. So with that mathematical model, we can then we can graph IL versus VL. And if we have any two plots on the graph, it's a linear relationship, any two plots on the graph, then we can plot the entire graph. So if we look at the VLOC, we've talked of that in past videos, that's our open circuit voltage. That's when the load here is open. So that's when our output, if there's no current being drawn, then our current is 0 and our output voltage is Vs. So that occurs here on the graph. Our ILSC, SC standing for short circuit, when our resistance here is 0 ohms, then the current being drawn then is just going to be Vs divided by RS, that series resistance of the voltage source, and that's right here. So as long as we know those two, then we have the entire graph here. And what moves us up and down this graph is when we change the load resistance. So this isn't not the voltage across the resistor. It's not our Ohm's law graph. It's the voltage at the output terminals of our practical voltage source as we're changing the load. So again, our practical voltage source, we can get to our current. Our current is going to be that ideal voltage source divided by the practical source's series resistance plus whatever the load resistance is. So we can find the load voltage using voltage division, because these elements are in series. And then at any point on the graph, we can get that current divided by the voltage. That's going to be our point on the graph, and that's going to be our 1 over RL. So it's as we vary RL, that's what moves us up and down this graph. The slope of the graph, however, if we look at that, the slope of the graph is negative 1 over RS. Again, we can find that slope using our 2 points, the short circuit current minus our open circuit current. That's our change in current divided by our change in voltage, which is our short circuit voltage divided by our open circuit voltage. So that gives us the negative 1 over RS. So why is the slope negative? We have to remember this is not an Ohm's law graph. This is as we're varying the load resistance. So as we increase the load resistance, it's open here. As we increase the load resistance, we're decreasing the current. We're decreasing the current, even though this resistor becomes higher, we're decreasing the current, and we get less voltage drop across this load because we lower the current. So again, increasing the voltage, decreasing the current, that's why we have a negative slope. So that's our practical voltage source. What we also need to look at is a practical current source. So that's an ideal current source, our circuit model for an ideal current source in parallel with the internal resistance. And because it's in parallel, we'll call that internal resistance RP. We also could consider that an output resistance, where here's our two-terminal device, where there's our two terminals, but the load sees, instead of a resistance in series with this current RL, we see a resistance in parallel. So the current's going to have to divide. Our current source our ideal current source supplies a current that divides. Some of it goes through its internal resistance, and some of it is provided to the load. Whereas, the dual of that was our voltage source, where the voltage divides. Some of the voltage divides across this internal resistance, and then some of it across our load. So let's further take a look at our uh, practical current source, and we'll analyze that like we analyze the voltage source. So again, this ideal current source, key here is that resistance is in parallel. So a current is the dual of a voltage, series is a dual of parallel. So if we can model that using a KCL, where the IL current flowing out of the top node here at the positive reference of VL, that's equal to our IS current flowing in, but what's also, again, flowing out is this IP, right? So we can call this IP. That's flowing out, so we're subtracting that. That IP is the load voltage divided by that parallel resistance, RP. Our open circuit voltage then, if there is no resistor here, it's an open circuit, then all of this current IS is going to flow through our RP, so that open circuit voltage is going to be RP times IS. If it's a short circuit, then all the current is going to flow through the short circuit, and none's going to flow through our IP here. So our short circuit current will be IS. And those are the 2 points on the graph that we needed to find in order to model IL versus VL of our practical current source. So our ideal current source at the output, our IL, no matter how we change that RL across it, the ideal current will always provide an IL of IS. But practically, what's going to happen is some of that current is going to divide as it goes through this resistor. So that's the dual actually of our practical current source. So if that load resistance is much less than this parallel resistance, right, well, current follows the path of least resistance. So if that load resistance is much less than the internal parallel resistance, then most of IS will go here, right? So for short circuit, all of it goes through RL. If RL is much greater than, so if our load resistance is much greater than the parallel resistance, then we're going to get no current to be flowing through the load resistor here. All of it's going to go through the parallel resistance. So if we want to deliver current to this load, we want this parallel resistance to be very high or to approach infinity. So our ideal current source has a parallel resistance of infinity. Whereas our ideal voltage source had a series resistance of 0. The last thing we want to examine here is if RL was equal to RP. Well, if RL is equal to RP, then these two resistors are in parallel, right? So then IL is going to be equal to our IL, which is equal to VL over RL, and IP is equal to VL over RP. Well, if RL is equal to RP, then these two currents will be the same, right? And then we'll be right back here, just like with the ideal voltage source. It'll be right in the middle of our graph there. So that's when we'll get maximum power delivered to the load, but we won't get the maximum current delivered to the load. So if we compare our practical voltage current source and our practical voltage source, these are IL versus VL graphs, we can still, both of them, we can look at the short circuit current and the open circuit voltage to be able to plot these graphs. Again, our ideal voltage source, the voltage would remain constant at all the times. Our ideal current source, the current's what's going to remain constant at all the time. But we see these two graphs look similar to each other. So what we're going to look at, is there a way to transform a model of an ideal, or excuse me, a practical current source to create a practical voltage source where at terminals VL and IL, it looks the same to the load. Because once we, well, if from the perspective of the load, we'll draw this over here a little ways, perspective of the load, all it sees is these two terminals. So all it cares about is the voltage across those terminals and the current being delivered from the terminals. So, how can we get these two graphs to look the same? So what we're talking about here is equivalent sources. When we're talking about equivalent sources, we're talking about equivalence from the perspective of the load. So we have the sources on the left, so looking in from the right that they're in fact equivalent. So our load voltage for our practical voltage source, that's just our ideal VS, ideal source there, we can by voltage division, times RL divided by RS plus RL, or it's equal to the load current times the load resistance. For our practical current source, well, then we can do a current division here to get our IL and multiply that by the RL. And so this is the current, right? This is our IL that we've gotten via a current division equation. So we want those to be the same, so they're going to be equivalent here if RS is equal to RP, right? Here we have RS and here we have RP. If RS is equal to RP, and if IS times RP is equal to VS. So here what we have is IS times RP, and here we just have VS. So if they're the same, if those two are equivalent, RS is equal to RP and IS times RP is equal to VS, then we have equivalent sources, and from the perspective of the load, we'll get the same output voltage and same output current delivered to it. So if we look at this example, are these two sources equivalent? Well, we can find out if they're equivalent just by looking at 2 points. So if we look here, we can say our open circuit voltage, that's if there's, it's open there, right? So our open circuit voltage is just going to be the 3 amps times the 2 ohms, or 6 volts. So, and our open circuit current, obviously, by definition, is 0. So when our current is 0, we're down here at 6 volts. If we look at our voltage source, our open circuit voltage, well, that's when our IL is equal to 0. We'll write ILOC. Our IL open circuit is equal to 0. So we get no voltage drop across this 2 ohm resistor. And so again, that's 0. We end up with just the 6 volts. So those points are the same. So now we just have to look at the short circuit current. So if what we're looking at is our short circuit current, then we will short this, right? And all of this, right, since that's a short, that current's going to be 0, and all of the 3 amps is going to flow this way. Why? Because there's our short circuit voltage, ISC, VSC, sorry, that's equal to 0. So if that's equal to 0 and it's in parallel with this 2 ohm resistor, there can't be any current flowing through that. So when our voltage is 0, our current is 3 amps, right? And over here, we have our short circuit. So if this is our VSC is equal to 0, then our ISC is just equal to the 6 volts divided by 2 ohms, or 3 amps. So because we see those 2 points are equivalent, then the 2 graphs are equivalent. So we can prove it with the graphs. What we can also show is that in this case, we do have, here we have our RP is equal to 2 ohms. Here we have our RS is equal to 2 ohms. So is RP equal to RS? Yes. And then if our IS, our P is equal to VS, here we have our IS is equal to 3 amps. Here we have our VS is equal to 6 volts and check. So we can just use this standard instead of even having to find the open circuit voltage and short circuit current. So we'll use this to introduce source transformations.